Okay, so quiz 19.1 on solutions and solubility. Question 1 is how many moles are in 5.12 grams of what we call copper sulfate pentahydrate. So the first thing we want to do is to find the molar mass of this compound. And the only trick here is that you'll include those 5 waters in the molar mass. And so when you're finding the mass, you take the atomic weight of copper, the atomic weight of sulfur, and then actually 9 times the atomic weight of oxygen. 4 of them in the sulfate, and then 1 for each of the 5 waters is a total of 9 oxygens. And then 10 times the atomic weight of hydrogen, because there's 2 for each of the 5 waters. In the end, this is 249.69 grams per mole. So that 5.12 grams, 249.69 grams for 1 mole, and that's going to be 0.0205 moles. So question 2 has to do with solubility. We've got 2 molecules here that are potential solvents for us to use. Water has highly polar bonds, and what's more, it has all of the components necessary for hydrogen bonding, so very strong intermolecular forces. And then the diethyl ether, so I'll draw it out here. I tried to give you a condensed structural formula on the quiz. Okay, there it is. Most of these bonds are non-polar, or at least so weakly polar that we call them non-polar. There are some polar carbon-hydrogen bonds, but just a couple, and on the whole this molecule, it may be technically polar, but it's pretty weakly polar. So both are solvents that would be used in a chemistry laboratory. Which of these solvents would you expect to dissolve wax? And paraffin wax and beeswax and there's 100 different types of wax, and they've all got their own subtle differences to their chemical formula. But just kind of a good example of a wax would be something like C45H92. Okay, it would be a non-polar molecule. It's a very large one, and so their intermolecular forces are enough to make it a solid at room temperature. But it's all London dispersion forces. It's a non-polar molecule. So the principle here is that like dissolves like. Water is a good solvent for ions and for hydrogen bonding species and for strongly polar molecules. It's not a good solvent for nonpolar molecules like wax or like oil. If you leave your candle out in the rain, it's not going to dissolve away, for example. If you pour oil into water, it won't mix in, it will sit on the surface. Diethyl ether, I don't honestly know how good of a solvent it would be for wax. I'd be interested to run the experiment, but I know that it would be better than water. Whatever amount that it could dissolve, I assume it would be a non-trivial amount, and it would be a much better solvent for a non-polar molecule like wax than water is. Okay, these next 2 questions have to do with concentrations. So find the molar concentration of 2.5 grams of sodium chloride are dissolved to make 15 milliliters of solution. The molar concentration is equal to moles of solute over the volume of solution. And so our molar mass for NaCl And it's a little frustrating that molar is a capital M for concentration, and then molar mass is also a capital M. So just want to make it clear, these are different capital M's. This is the molar concentration. This is the molar mass of sodium chloride. 58.44 grams per mole. And our 2.5 grams then, .44 grams is 1 mole. This is going to give us 0.0428 moles. And if we wanted to turn this into a molar concentration, we'll divide by that volume in liters. That 15 milliliters, to convert that into liters, we simply divide by 1,000. We get 0.015 liters. This will give us a molar concentration of 2.9 molar. 2.9 molar. Ultimately, we only get 2 sig figs for that answer. 2.9 molar. And the question 4. Find the mass percent for 0.75 grams of naphthalene dissolved in 5 grams of dichloromethane. So this is going to be the mass of the solute over the total mass. So that'll be solute plus solvent times 100%. So our mass of solute of naphthalene is 0.750 grams. And the total mass would be the dichloromethane plus the naphthalene, 5.750 grams. 5 grams of dichloromethane solvent and 0.75 grams of naphthalene solute times 100%, and that is equal to 13.0% with 3 sig figs. And you'll notice we didn't need to know the formula or the molar mass of either the solvent or the solute. The mass percent just depends on the masses, the total masses. And one last problem. Solvation of sodium hydroxide is an exothermic process. What that means is NaOH solid solvating to produce Na plus aqueous plus OH minus aqueous. They split apart. If it's an exothermic process, then using our trick from the Chatelier's principle, we'll add heat as if it is a product. And so if I were to increase the temperature, it would be as if I'm adding product and shift the reaction over toward reactants. It would be less soluble at high temperatures. And so if I decrease the temperature, that's as if I'm removing product, shifts everything toward the right. And so we should lower the temperature to increase the solubility of sodium hydroxide. There are plenty of salts that are endothermic in their solvation energies. Some of them are exothermic, and so it's not universally true that increasing the temperature will increase the solubility. Although there is a good majority of solutes, at least in water, that are endothermic in their solvation process, and so increasing the temperature will generally increase the solubility of solutes, but there are certainly exceptions to that rule, such as sodium hydroxide. Okay, that's quiz 9-1.